Long title. All right, thank you. Yeah, the title actually is only part of the talk, so let me get started. First, thanks to the organizers for the invitation. It's a fantastic meeting. I really like coming to this meeting, and Edinburgh's great. Okay, so I thought I'd just start a little bit with a slide about Livermore, where I work. If you've never been there, this is just from the web page at some point in time. It's 1 square mile, about 9,000 employees. And I've been fortunate working there that I've been able to work with some of the largest supercomputers in the world. We have the #1 computer at the moment, El Capitan. When I first started doing parallel computing, this was like in 1989. They had 128 processors on an Intel Hypercube, large at the time. And this is billion-way parallelism, so really come a long way. You know, the power required for this thing is equivalent of like 30,000 homes to power, something like that. It's crazy. And here's the building that it's housed in. And my office is right there. Okay, that's just quick about that.
How can one get an invitation to visit? How can one get an invitation to visit?
You're welcome to visit anytime. Let me know.
Doesn't do much when you look at it.
Yeah, so Max.
So the hyperbolic problem part is going to be here. But I thought since I do multi-grid methods, that's what I've done most of my life. I thought I'd start with multi-grid methods. That way you can kind of get a sense of where I come from when I do parallel time, because it is multi-grid in time. So we'll do that, and then I'll actually, if you know, hopefully I'll have time, and we'll get to the point where I'll preach to the choir a little bit about parallel time. Okay, so we're going to start real basic. This is just a cartoon to show how classical multi-grid works. Think of a Laplacian. It's an iterative method. You have an initial guess, you have an initial error, and I'm plotting something here like that. There are 2 components. One is relaxation, so something like weighted Jacobi, Gauss-Seidel. You just do a few iterations of this. What happens to this underlying error is it gets smooth in the classical sense. So you can approximate it accurately on a coarse grid, which is a smaller system to solve, right? And then if you do the correction step after this, you get very fast conversions. The problem in practice, though, is that this can be still billions of degrees of freedom. So what we do is just reapply this idea, do more relaxation, and you go all the way down to some really coarse system. Sometimes this is, well, I guess in Boomer AMG, it's like a 9x9 system. It can be just a single equation, actually. And then you interpolate all the way back up. Oops. And that's a V cycle. And we have a lot of methods that we've developed since like 1998 when Hyper came out for the first time. And we feature multi-grid methods in this library. And the reason we do that is because of these big computers and trying to solve systems on them, they have O of n complexity. So you do O of n work to solve for n unknowns or DOFs. And so it has good scaling potential, right? Okay. So that's multi-grid sort of from a cartoon perspective. Algebraic multi-grid is a big thing we do as well. And this is based on multi-grid principles, but the idea is to just use the coefficients of a matrix. So you don't have grids anymore. Instead, you have to use the graph of the matrix and coarsen that in some way with an algorithm. It has to be a parallel algorithm too. And another difference with algebraic multigrid and geometric multigrid is usually with geometric multigrid, you construct the coarse grids first, the coarse grid correction step, and then you have to select your relaxation scheme to complement that so you get good behavior, right? It's the opposite with algebraic multigrid. We usually fix the relaxation method, be a simple thing like weighted Jacobi, and then you have to construct the coarse grid correction. That's where all the research comes in to complement that well. And one of the things that pops out when you do this is that, you know, what is algebraically smooth that complements the relaxation process is not always geometrically smooth. This picture shows this. Again, it's just a Laplacian-like equation. It's isotropic on the left half plane and anisotropic on the right. And after you do a few sweeps of Gauss-Seidel, this is what the underlying error looks like. So you can see on the left, you could do full coarsening where you coarsen in every other direction. But on the right, it's only smooth in the x direction. So you really only want to coarsen in that direction. That's called semi-coarsening. And these are the grids actually that AMG will pick when it does its coarsening algorithm. It knows nothing about grids. It's just looking at coefficients. And I've just plotted it on top of the grid so you can see it. The larger squares are for the coarser grids here. So that's important. And then the other big thing is constructing the interpolation operator. And all the algorithms that we develop are based on what's called a weak approximation property. This is convergence theory, basically, in very summarized form. You have a two-grid error propagator that you measure usually a norm, because A is SPD a lot of times, but there's non-symmetric versions of this theory as well. So it's less than 1 minus 1 over k, where you want to make k small. 1 is the smallest you can make it, and that's perfect. And this shows you what interpolation needs to interpolate well. So if you let E be an eigenvector of A and associated with a small eigenvalue, then this denominator is small. So you need to make the numerator small, which means that you need to interpolate this error well, because you're comparing it to this is restricting it to the coarse grid and then interpolating it again and then comparing it to itself. And so that has to be very accurate. And so what we really have to care about is the near null space, things that are very, very small items. And you have to actually kind of assume things ahead of time about that normally, with the exception of this one method called adaptive AMG, where we try to discover these near null space modes on the fly as we do the algorithm. Okay, so that was, I just showed that on a structured grid. This all works for unstructured problems as well. This is just showing a few examples in 2D. And these two on the left have an anisotropy in 30 degrees, and you can see these, you do get the semi-coarsening that's sort of orthogonal to that direction that pops out. And then over here, you get the isotropic coarsening that you'd expect to get. So very nice. Something about cycles. I showed you the V cycle. That's the one we typically use because it's the one that's scalable, that works best in parallel. So this kind of limits our choices, parallelism. They have this W cycle and FMG cycle, which are also big in the original sort of work. They're more robust, but we really can't use them because of the parallel issue. And an interesting thing about the FMG is that you can solve to discretization accuracy with O of n work. But it's very hard to construct a method that actually does this. And so it's an interesting research topic, though, especially if you want to. There's also ideas we've had in the past about how we might be able to get this log squared n down to log n in parallel. I'd like to go back to that topic at some point. Okay, so again about parallelism. You have all these coarse grids and you know, billion-way parallelism on these machines, right? So how do you parallelize it? It turns out that just the sort of naive way of just parallelizing things works as best as you can expect. So I've just shown a little cartoon again here. This is 4 processors dividing a 2D problem. Okay, and if you just coarsen, this is what happens. And you can see that on the coarsest grid, I've got idle processors, right? So on a machine like an earlier machine we had, that would be order, you know, 1 million idle processors. Seems like that would be a problem, and a lot of people have done research to try to take advantage of the fact that you have these idle processors sitting around, but it really isn't that useful to do that because all the work is being done down here on the fine grids. You really don't spend hardly any time on these coarse grids, so it's really, you really can't get much benefit from doing this. So multigrid has a high degree of concurrency. That's why we like it. In fact, the only sequential part, and if you design it well, is just O of log n size. And that's often the minimal size you can achieve. There's even theory like from 1992 that shows the lower bound, this lower bound for like the Laplacian, independent of algorithm. This is the fastest you can do. And if you then look like a parallel computing model, you also see the O of log n pop out in the right place. So these first 2 terms are for communication using a standard postal model. We have a latency cost plus something associated with bandwidth. And you can see the log terms here. And then you have some sort of flop rate on the right. And, you know, it's nice to have a little cartoon that says all these things, but we also have code that demonstrates that this is, you know, 1.1 million cores from, again, this machine I just mentioned on the previous slide. And everything holds together. You get nice scalable results with this algebraic multigrid method. All the lines are just using different combinations of threads and MPI tasks. So at the time, it depended on how you know, made those choices that, you know, you get work performance over. Okay, so that was a quick overview of multigrid. Now I'm going to switch to multigrid in time. Which does change the story a little bit, but now you can see my perspective. Okay, so it'll be multi-grid reduction, which you all have heard about. You know, we think of this all at once system, usually with the identity on the diagonal for grid. And phi is our time propagator. And the method is based on an old idea called multi-grid reduction, dates back to the late 70s. And we're just using this and extending it in time. So here are some of the components of that. If you take your temporal grid and draw it here, and you have a coarsening factor M, that gives you a decomposition of the fine grid into what we call F and C points. And this is just AMG terminology. You literally see that in AMG. So the F points are in between these larger intervals, and our coarse grid is actually lines up with the red points here. Yeah, C points. And then you have the two components of multigrid. You have relaxation, and the method for relaxation that we use here is it alternates between so-called F and C relaxation. F relaxation is shown here for one interval. You start with the leftmost data in the interval, and you just integrate to each one of the F points inside the interval. You can do that in parallel, so that's where the parallelism comes in. C point relaxation is the same, except you start at the last F point and you integrate to the C point, and you can do that in parallel. The coarse grid system, in sort of the standard default approach, you just rediscretize on a coarse or temporal grid. That doesn't always work, and that's what a lot of this talk will be about, is doing something different on the coarse grid. But the reason we like this is it's kind of it has a potential to be non-intrusive, because everything that I've described, especially in the relaxation process, is just wrapping a time stepping operator, right? At least in our approach, we just solve the same space-time system. XBraid, I'll mention on the next slide. That's our open source implementation of this. And the big research question is how you define the coarse grid. And I will come back to this again in the hyperbolic setting. So the perfect coarse grid system is what we call ideal. It comes from the ideal interpolation and P transpose AP on that, or RAP here. It's not practical because you have this phi to the mth power in the subdiagonal here. It still has the right structure. So this is too expensive. And so what we want to do is approximate this with a sparser, cheaper operator that's still spectrally equivalent to this in some way.
It's also the Schur complement, right?
It's also the Schur complement, correct. This is what we need to do for mgrit, and that's different from what we usually do in AMG. AMG is focused on constructing this interpolation operator. Here we have the perfect interpolation operator, and it's easy to actually use it. We're just doing this integration to these F points. It's trivial to actually use it in practice. But instead we need to approximate RAP because it's not practical. And we can do this in AMG. We do have something we call non-Galerkin. It's used some, but it's not the main research component of XBraid multi-grid research. Okay, XBraid is our implementation of this. It's designed to be non-intrusive, as I said. So users basically have to write this wrapper around their time stepping routine. One step in braid. We have some features where we can kind of minimize memory use. So if you do the right things, you can have per processor the same memory use essentially as time stepping would. So you don't have to pay more per processor. So you get the extra parallelism as well as the extra memory, but you use it the same way. And then we also try to do fancy things inside the code where we overlap communication and computation. So this is, say, a window of the time interval that one processor owns. The first thing you do is post or receive to the left, do some computations on the right and some to the right. And then while you're waiting for that communication to finish, you do some computations in the middle. And then, when it finishes, you can do this leftmost computation to finish up. And all the kernels in XBraid are designed this way. So the whole idea behind mgrit is to try to help users who have very complicated codes transition to parallel time, right? And that's really why we've designed it this way. It's not the end game. I mean, once everybody has accepted parallel time and they're using it, there's no reason to do this method. But this is the hope behind it, is to give people an easy way to kind of transition into it because it's, at the end, I'll talk about this paradigm shift, which you all know. And yeah, that's what that's about. I've showed linear, but obviously we can extend all these ideas to nonlinear because I'll talk about some nonlinear problems coming up. I mentioned XBraid already, and we've done lots of research in the context of MGrid on a variety of applications. We also have looked at how to do adaptivity in space and time, as well as space-time together, moving meshes, and then we practiced wrapping codes that were existing codes that people have written independent of all this stuff. So we can learn and improve the library. Okay, so now I'm finally to the hyperbolic problems. So these are the three collaborators on this work. Oliver really is the person who did most of it. He was a student and a postdoc, and did most of this work. Yeah. So I'll start a little bit with some insights that sort of came out of the work in the very beginning. There's sort of two important things we learned between MGrid to try to solve hyperbolic problems. And they're given here in blue. The first is that, we already coarsen in time in MGrid, and what you should not also do is coarsen in space for hyperbolic problems. And this picture sort of shows why that's true. It's a simple advection problem here on a uniform space-time mesh. Upwind first order discretization, but this is there's no discretization error for this problem because everything lines up with the grid points, and actually these are just a bunch of lower bidiagonal solves along each characteristic direction. So if you coarsen in both time, every other point, as well as space, and that's your blue squares here, what you can see is that some of the characteristics drop out, the ones in black in particular. So you get no coarse grid correction from them. And so basically your convergence goes like O of n, the number of points you have in time, which you don't want. So you don't want to also coarsen in space. That's the first thing we learned. And then the other thing we learned is that the coarse grid operator has to be a very specially constructed operator. It looks semi-Lagrangian-like. What I mean by that is the non-zero pattern has a similar non-zero pattern to what you get from a semi-Lagrangian discretization. So the first thing we did was just for proof of principle, where what we did was use an optimization technique to construct these semi-Lagrangian-like operators. We defined a non-zero pattern and solved this optimization problem. Then we showed that we could do high order, implicit and explicit, multi-level, and get speed up. But this was not a practical approach. Turns out this is something I want to revisit now, because I think this is the way, a general way of maybe getting doing this in a non-intrusive way. It's related to what Daniel talked about. Maybe you could do machine learning, for example, as one idea, but there's other approaches for constructing operators you might consider. Okay, so let's start with linear advection, 1D and 2D, even though I'm showing 1D here, variable wave speed out front. And I mentioned semi-Lagrangian like operators, so like that would be a good choice for getting a practical. It has a nice property. There's no CFL limit as well. Turns out, though, you can't just use semi-Lagrangian on the coarse grid and solve the problem. It won't be conversions. You have to do something more. I'll talk about that on the next slide. And if you want to know more details, the first two papers here is what you need to look at. So this is, in a nutshell, the semi-Lagrangian, the modified semi-Lagrangian approach. So first with semi-Lagrangian, what is that? So if you go from time n to time n+1, you want to compute a value here, this space-time point. Semi-Lagrangian basically solves a backward problem to get an estimate for the departure point of the characteristic. And then since it doesn't line up with the grid, you just do higher order interpolation nearby. So this point here depends on data that's around the departure point. That's your stencil that you really want to have. And standard discretizations won't have that. To modify it, so this is the psi is our coarse grid operator. I'll use that terminology here. So this is the thing we want to approximate phi to the m. We just multiply by this operator b, which is here. And what b is doing is like doing backward Euler on this equation here. So if you have a first order Lagrangian, a semi-Lagrangian discretization, so P is 1, this is just diffusion. So what you're doing is you're adding a little bit of diffusiveness to the semi-Lagrangian sensor. This parameter zeta has to be computed from some a priori truncation error analysis. And the way we do the inverse part here is we just do a fixed number of steps of GMRes. This is how we do all that stuff. And the reason we do it is what we need to do is actually approximate phi to the m to one order higher than the actual original discretization phi. So phi has is order, p. Psi is all semi-Lagrangian is also order p, but they need to approximate each other to p plus 1. Yeah, okay. So you can actually show also in a simple setting that semi-Lagrangian by itself won't work. So this constant coefficient advection again. I'm doing first order here. You can get the similar pictures for third or higher order. And what I'm plotting is convergence factor and CFL. Okay. And the colors here are different coarsening factors. So black is coarsening factor of 2, all the way up to coarsening factor of 64. And here what you can see is that you get divergence for many CFL numbers on the left if you just use the semi-Lagrangian approach as your coarse grid operator. If you modify it, however, with this B operator I just talked about, then everything converges to 0.25. So the scale has changed here, independent of coarsening factor. So you really need to do this or do something.
What was first? You mean it's just use a constant function for doing the interpolation? Is that what makes it first order? You said P is 1.
No, this is the semi-Lagrangian discretization.
That's just the interpolation rule that you used to.
Yeah, I guess it is. Yeah, I guess it is. But again, you can get similar pictures for the higher order cases. Okay, here's some results, just quickly on one slide for a variable wave speed case. In 1D here on the left for this equation with this wave speed, wave function. And for different orders, you can get speed up. These numbers here show that. And we can also do it in 2D. So we get some speed up. And so this is showing a couple of time snapshots of the solution here. They're both periodic. So this guy kind of moves to the bottom right and then back to the center and then to the upper left and back. It kind of sloshes back and forth, the solution to the problem. So that's all good. And we're going to use that. The fact that we have this semi-Lagrangian method for solving linear advection equations is going to be used over and over here. In the nonlinear case, as well as systems that I'll show you. So we're going to switch to nonlinear now. Now we have this problem here, this conservative form, and I'm going to consider problems. One is inviscid Burgers. We'll indicate that by B, and then Buckley-Leverett is the other one. And the only difference between these two is this flux functions. Put here. So the discretization will be explicit Runge-Kutta, finite volume and space with this Lax-Friedrichs numerical flux. We'll have 2 orders that we'll consider. The third order uses a Wino scheme, and then we'll also use 2 approximation techniques for the Lax-Friedrichs flux, global and local. Oh, okay, yeah. So this is what we want to do. The first thing we did, just stepping back for a second, when we wanted to move to nonlinear problems, was we wanted to extend this in the usual way we do for MGrid, where we just do nonlinear multigrid. But when we looked in the literature to try to find out how to do semi-Lagrangian for nonlinear problems, we only found a couple of things in the literature. And in both cases, they had CFL limit constraints, which is something we don't want, obviously, here. So instead, we have a different approach that we will use from now on through the talk. And it's basically an inexact Newton method, where we'll take our linear MGRIT method and apply it to the linear problem. At least, and we'll also have to do some special things to sort of get a linear problem that has the right form so we can apply MGRIT to it. That's part of what the slides will be about as well. Okay, so here's our nonlinear system. These are all nonlinear fees now. And the basic iterative method looks like this, where we have this linear preconditioner PK that you'll see pop up again and again, because we want to choose this in a certain way. If you let this operator be just the Jacobian, then you just get Newton's method. So if you basically the subdiagonal here, these phi lin operators, if they are just the Jacobians of phi, then this is just Newton. But we're going to instead construct approximations to these Jacobians and use that. This is pseudocode for the algorithm. Ignore that step 2 for a minute. You compute a residual, and then we have 2 things we'll consider: solving, computing the preconditioner exactly, or doing it inexactly by doing 1 V cycle of this linear modified semi-Lagrangian method. Okay. And we have this extra thing we do in all of the results. It's this sort of a nonlinear F relaxation. It tended to give us some better robustness overall, but in most of the cases, a lot of the cases, we really don't even need it. But we did it for consistency in the results, just to let you know. Okay, let's see, what else do I need to say? That's good. Okay. All right, so constructing this P it's important to do it in the right way. And so here's showing what needs to happen, or a couple of things we do in the 3rd order case with the Wiener scheme. In the Wiener, you have these solution reconstructions that have to happen at the cell boundaries. So say cell I plus a half, from both the left and the right, you have these cell reconstructions that have to, these solution reconstructions that have to happen. And so if you take the gradient of this is what you get. And the first term is exactly what you get with the Wiener scheme. It has these Wiener weights in it, and it's a very complicated method. And then you get this other term here, which involves the gradients of the Wiener weights. And this can be expensive to compute. We could do exact Newton, especially for the global Lax-Friedrichs case. But instead, we consider approximations to it. And the first one is just to take the first term, we'll call that Picard and call it P, indicated by a P. And the second is to do an approximate Newton, where we just do a numerical differencing type estimation of the gradient. Okay. And the reason this is nice, all of this is nice and works for us is, again, P, if you look at it, it looks like a linear advection equation. So we can reapply our modified semi-Lagrangian scheme. So here's results. This is Burgers, inviscid Burgers on the top, Buckley-Leverett on the bottom. Just to say a couple words, well, here's the solution so you can see them. I guess the main things to point out is you have shock wave and a rarefaction up here, and down here you have compound waves. And this is a harder problem. You'll see the convergence is a little bit worse for the bottom case than the top. Okay, so 1st order results. Let me explain everything that's here. Probably should be using my glasses. Top row is again Burgers, bottom is Buckley-Leverett, and I'll show a bunch of diagrams like this where you have iteration count on the bottom and relative residual on the left. Okay, and we're looking at a weak scaling sort of case. So the black colors are the smallest case, where the number of points in space is 64. The light blue is the largest, where you have 4096. And we also have dotted and dashed lines. So the dashed lines are when you solve the preconditioning system exactly, and the solid lines are when you apply the 1 V cycle of MGRIT to it, so the solid lines is what we really want, because that's the methods that's going to perform well in parallelizing and give us speed up. Okay, so in this slide here, I've got the global Lax-Friedrichs case on the left and the local Lax-Friedrichs on the right. The thing to notice in all of this is that the iterations are bounded. When you do this weak scaling thing, they approach kind of a limit, is what we want. Another thing is that the number of iterations for Buckley levers is more than it is for Inviscid burgers. But the convergence is good in both cases. And another thing I want to point out is we're going to like 10 to the minus 10 here, which is way beyond discretization accuracy for this problem. If you actually take a more careful look at it, it only takes a few iterations really to converge for all of these. And I've got one little outlier set of things that are being plotted up in the upper right, just to show you again that you really need the modified semi-Lagrangian. You can't use just semi-Lagrangian here, and that's what these dotted lines are. The convergence isn't nearly as good. In fact, for the green case, you can barely see it there. It just goes straight up. So the modifications important. That's the only time I'll show that. Third order is similar. The bottom line is similar. Here it's a little bit different because it's all local lax Friedrichs, and now I've got these two preconditioners I talked about. The one that was the Picard on the left, and then this approximate Newton where we did the differencing. So again, we get, the number of iterations is a little bit higher than in the previous slide, but again, this is way over solving. So you still get good convergence and it's bounded. Okay, so doing all right. Now I'm going to switch to systems, and first I'll go back to linear and do acoustics. Okay. The idea will still be the same. We're going to try to use this modified semi-Lagrangian method on the inside, but we have to do more in the precondition. And the method is still going to be this preconditioning idea. We're constructing this P operator. So here's the acoustics equations. Unknowns are pressure and velocity, and we have a couple of parameters: density, bulk modulus. And in the numerical experiments, we'll write the parameters in terms of sound speed and impedance, which have this relationship to the original here. Turns out that this is equivalent to a pair of decoupled wave equations. So by solving this, we're effectively solving wave equations. The discretization here is going to be first order Godunov. And if you want to see details about this, it's just got accepted. This one just got accepted about a week ago or something. Yeah, the previous one, I forgot to mention that one also got accepted like 2 days ago. So they both appear in CISC. Okay, so one of the important things we do here to try to get to this point where we can reuse our modified semi-Lagrangian is this transformation to characteristic variables. So if you take the A coefficient from the previous slide, this guy right here, and you do an eigendecomposition in this way, then we make a change of variables to these W variables in this way involving the R naught. That gives you a new system to solve of this form, and all you should do is just look down here at the system. Okay, it's the same as this one here. And the thing to note is on the left, you've basically got two decoupled wave equations, advection equations, with a negative sound speed on the top and a positive one on the bottom. And the only thing that couples them together is this right-hand side here. And in particular, if you think about the constant impedance case, it's right inside zero, and you really do have two decoupled equations. And so the more variation you get in this impedance, the more the coupling between the two systems, and this will affect the convergence. But this gives you a sense of what we're going to do for the preconditioning. Right? We're going to use the fact that we have this largely diagonal type system. So the way the method works, it still uses this residual correction approach I showed previously in the scalar case. But first thing we'll do is do a transformation. We'll take our original system, we'll transform it to these characteristic variables. So we'll have hats in that case. Here's the system in 2x2 block form. If you have the constant impedance case, these off diagonal blocks are zero, and you get that decoupled set of advection equations. Okay. And so instead of solving this thing directly, what we're going to do is precondition it. And so we have two approaches. The one on the left is to use the diagonal. And the one on the right is use a lower triangle. So this is like a block Jacobi, and this is like a block Gauss-Seidel type thing as your preconditioner. And we're gonna have to do one more thing though. Diagonal blocks here with the hats actually are not perfectly right for our modified semi-Lagrangian. We have to end up dropping some terms and put a tildes here. I won't tell you the details. You can look at this paper. So these are the preconditions we'll ultimately want to use, this P tilde with diagonals and P tilde lower triangular, and solve the diagonal blocks with 1 V cycle of M grid again. So that's something we can actually get good performance and parallel speed up with. All right, so here's some problems, 4 of them, increasing difficulty from left to right. The one all the way to the left in black is your impedance, so it's constant. This is the decoupled case where you have the 2 convection equations, and then you have sort of smoothly varying impedance, and then these have jumps in them. So I'll start with the first 2. First one's on the top, second one on the bottom, and looking at different preconditioners. In the first column, it's the p hat precondition where we just invert them entirely. We don't do any multi-grid reduction in time, no M grid here. Because the preconditioner in this case is exactly the same as the operator, then you just get 1 iteration convergence in this case. Down here, you still get good convergence. Let's see. Yeah, so if you want to see the difference between the diagonal preconditioner and the lower triangular, it's dashed lines versus solid lines, okay? And then right here is where we do the P tilde change on the diagonal. Again, it's the same in the top case, and you just get 1 iteration. And here it works well. And this final thing, this final set of results is what we really want to do in practice, where we do 1 V cycle of M grid, very inner solve. And you get good convergence here as well. And the story is the same for the other 2 cases. They take they take more iterations to converge. Especially in this last case, you can see the iteration counts are larger, but they're not bad in the lower triangle in the preconditioner with the L. That's the solid lines down here. Okay, and all right, yeah, I'm doing well. So I'll actually kind of run through these last results pretty quickly. The stories, because the story's effectively the same. Now I'm actually doing nonlinear and shallow water as well, and Euler are the 2 problems I'll show you results for. And the test problems are parameterized in the following way. The initial conditions basically have a bump that you can add to them with an epsilon parameter at front. So if epsilon is small, it's a small bump, and if it's large, it's large. So the water height in the case of the shallow water equations, and also the pressure in the case of Euler. It's first order of finite volume discretization in this case. Okay, and here are results. This is for the shallow water equations. Epsilon equals 0.1 here, epsilon equals 0.6 here, so the bottom one's the harder case. And there's lots of lines here, but sort of the same story. Convergence is good, and it seems to be bounded independent of problem size, and it degrades with larger epsilon. That's sort of the story here. And same for Euler. See. Yeah, the dashed again are yeah, this one jumps up a little bit here at the end, but yeah, anyway, the results are pretty good, we think. Okay, so that's the hyperbolic part of the talk. Now I'm going to switch gears a little bit. This first slide came about after Martin's talk yesterday. I think it was yesterday. Anyway, there's this relationship between mgrit and parareal that where they're basically the same under certain configurations, right? But they're also not the same. And I constantly get confused when I see parareal talks and vice versa, I think, for the parareal community. And so I decided to make this view graph, and hopefully I get the story right. This is at least my perspective on it, just to kind of give you an indication of why that's the case. Okay. So for mgrit, it comes from a multi-grid perspective. And as Martin said yesterday, parareal is really, he thinks about it as domain decomposition. So it's two different ways of thinking about approaching the problem. So in the multi-grid case, as you saw, we're obsessed with O of n and scalability. That's all we think about. In the DD community, I think there's more of an emphasis, even though scalability is important, there's more emphasis on robustness. So you want to develop a method that converges well for large classes of problems. And so there's a slightly different ways of thinking about the problem. There's also a history in the DD community, the Schwartz, the old Schwartz algorithm, which starts with two domains, I guess. So there's that. And this is what leads to some of the differences in the two communities. So in the case of multigrid, we think of having a fixed coarsening factor. M is our coarsening factor for mgrit. And so what does that mean? I've sort of drawn pictures down here. It means that our time windows on T sub I have a fixed number of points in them. And so if you think about scaling things up and letting dt go to 0, then these things are shrinking. They're getting smaller and smaller. You're getting lots more and more of them. Whereas in the domain decomposition setting, the windows are sort of fixed instead. And so if you think about changing dt, that means you're changing your coarsening factor. And it means you have more and more points per window, time window. And another difference is that we naturally we have a multi-level method we're always thinking about because of this O of n thing. And typically in the domain decomposition community, 2 or 3 levels is what you mostly see. So that's kind of it's sort of the philosophy is a little different, even though the two methods can be the same. And this leads to us coming to different conclusions, or in Martin's talk, I was confused actually with the diffusion problem where, you don't even need the coarse grade correction. And this kind of explains
The domains remain fixed.
Yeah, the domains are fixed in size. Martin said T equals T 1/2 or something. Yeah, so that's the length of this thing. And which means if you change dt, you're just adding more points here. And it all makes sense if you think about it that way. But I was confused because I kept having this in mind. And here the domains would be shrinking and it wouldn't work and behave the same way. Another thing that came up is this was at the Switzerland meeting. I think when it was asked, why are we still trying to solve advection problems or hyperbolic problems with parallel time when Martin's already proved you can't do it? It's paper here. That was a good question. It was very confusing to the community, especially to us, because there was the first theory paper for mgrit had provable examples of conversions for hyperbolic problems, advection problems. And the reason is the same kind of reason is here we have constant coarsening factor. And in this proof, on the fine grid, you assume it's exact.
It's exact.
Right. So it's like having an infinite coarsening factor in a sense. Right. So there's sort of two different settings. And both proofs are correct. But it leads you to think that different things about what you can do and can't do in solving problems. So anyway, hopefully that was a useful thing for everybody here. I made it yesterday. So
Oh, good.
if you have ways I can improve this further, let me know. Okay, and this last part, I'll just kind of preach to the choir a little bit, but give you my perspective on parallel time. So I like to call it an approaching paradigm shift, right? Because I think it is. I think it's inevitable. This is one way to show this. If you can just take a simple heat equation, you can show both with strong scaling and weak scaling that eventually parallel time is going to be the faster way to go, right? But we also, Jacob and I wrote a little tech report that I thought I'd mention here. You can actually look at it on the Braid Wiki Publications Wiki, where we did a proof that this is inevitable. And the reason we did this is I remember talking with somebody who was very skeptical about parallel time. And I told him at some point, I said, you know, if I make certain reasonable assumptions, I'm pretty sure I can prove that this is something we'll have to do. And so that's what this proof does. It makes some assumptions, and the idea is you accept these assumptions for the proof, and then the proof is simple. But this helps to frame the discussion, I think. So just quickly, the first one is that the number of points in time is going to continue to get larger and larger. We move forward in the future. Tau is our actual time, like the date, right? So as the date changes, these numbers will get larger and larger because scientists just want to see more and more detail. And then the other two in the middle is that time stepping is linear in the number of points in time, and parallel time is polylogarithmic in the number of points in time. I think these are both also reasonable assumptions because we can show that we have methods that do this, and I think it's pretty natural to see that time stepping is proportional to the number of time points. And then with these assumptions, and one final assumption is that, the time to solve a problem using sequential time stepping, if that gets slow enough, so if it gets larger than some parameter theta, threshold times how long it takes for a pint, every scientist is going to have a different threshold theta, but I think every scientist would. Then at that point, they'll switch to parallel time. And given these things, that you can prove that this is going to happen. And it actually, something interesting came out of this that I didn't realize before, which I'll mention, is there's this atomic time T naught that I've written here. And I like to think of this as clock speed. That's one thing you can think of. And we like to say clock speeds have stalled, and so we have a bottleneck, and that's why we need to go parallel time. But when you work through this proof, you realize that this doesn't matter. Even if the clock speeds are changing, eventually people would still make the switch. So that was something I didn't expect, and so it was a useful thing. If you're interested, give it a read. Okay, and then this is the paradigm shift. Okay, so obviously, you all know this. I'm preaching to the choir, but now we have to converge to the solution in space-time, right? And so this is the hard challenge for parallel, is constructing algorithms that do this. Whereas before, nobody had to worry about that. You had to have a stable discretization scheme, and then you just do time stepping. Another thing that changes, though, is the choice of the scheme you make. So I argue that there's no difference now between implicit and explicit with respect to parallel time. If you just draw a simple 1D space-time setting for an explicit stencil, this would be the explicit case. Point in time depends on explicit on 3 backward in time, and here's implicit where you have to solve a system that's tridiagonal, just to show it here. From a multi-grid perspective or any sort of space-time perspective, this is just a 4-point stencil that approximates the same PDE. And so the algorithms for solving these are computationally similar. So people will make different choices, I think, in the future because of that.
I was just gonna say, and we can start using stencils that look forward in time too, right? Because we have access to the whole trajectory, right?
Computational steering is something a lot of people do. That would change. A lot of people will run a simulation up to a point, and then they might have to change some things, especially if you think Ale and meshes tangling.
I've only seen that at Los Alamos, but I guess you've seen it.
We have it at Livermore too, but I assume there's probably some other applications where people have to do some sort of steering. But it changes here because you aren't doing time stepping, so you have to do it in a different way. Full space-time adaptivity is commonplace now. So Hans mentioned the space-time adaptivity and the structured adaptive mesh refinement community. That's really the only community that I know of that does this right now with time stepping. But now anybody can really do this if you're doing full space-time. And then the other thing is method of lines isn't really something you'll have to do anymore. You could have completely unstructured space-time meshes, right? So that also changes the game in a lot of ways. And there are people who are doing space-time finite element methods and studying these kinds of things because yeah, the paradigm is shifting. So that's it. Just went on. That was perfect timing. These are just conclusions. I don't know, it's just repeating what I said. I don't really like conclusion slides too much. Yeah, we had a couple of insights we had to make for solving advection dominated problems. Future work. So for me, the big one is coming up with a way of solving hyperbolic problems non-intrusive. If we want to do the whole mgrid, xbraid thing and help people transition, then we need to figure out how to do that. So, and it's something we're trying to get funding to work on this. And otherwise, these are some references that of the papers that I mentioned during the talk, and I'll stop there.
Questions?
Yes.
Your mapping to characteristic coordinates is not dissimilar to what we like to use when we do the shallow water equations with the exponential operator. They're equivalent on some levels. So is it true then that your interesting convergence plots for these hyperbolic problems, you are doing that in the map space along with characteristic curves, right? So that's similar to what we do for our oscillatory.
Modified semi-Lagrangian method is being applied in the characteristic variable.
That's right.
setting. Yeah.
That's right. So we have a modified equation too that is, we're doing some averaging because our nonlinear term is causing low frequency oscillations too. And our shallow water equation is just slightly different than yours in that we have a rotation component sort of into the board. It's still 1D, but it also causes there to be this fast singular thing in the solution, even though we're just doing it locally. But I feel like it would be very interesting to.
We're going to be at
Yes.
Bay Area, so we can.
Yes, in October, I'll come by.
Okay.
With that characteristic-based preconditioner, that you linearize from the fine grid, so from the non-linear level, you get the linear Jacobian, and then you write the characteristic preconditioner, and then you're doing a V cycle on that preconditioner.
Yeah, it's in the linear. Yeah, the V cycle is in the linear.
Okay, so you're not converting to the characteristic components at each level and then transferring and then.
No. Yeah, so it's the outer flavor of the method is still an inexactly type thing.
Okay, so it's a preconditioner
It
for.
would be interesting to go back to the nonlinear multigrid idea at some point.
I mean, it's a preconditioner for the linearized Jacobian that you're doing solving with multigrid rather than at each level of a multigrid of the linearized operator. You're doing a characteristic save.
Yeah, we're not. Yeah, it's not nonlinear multigrid.
I have a practical application in mind in groundwater flow where you have some regions where you may be governed by diffusion, other regions where you are convection dominated. What would be your suggestion to treat this with using parallel time? Do we need all this Wiener stuff to?
No, the Wiener scheme was just the way that was discretized. We try to be agnostic to the discretization that's being used, but this is still an intrusive approach. So when we change the discretization, we do have to do a little bit of extra work to rederive this modification that we need for the semi-Lagrangian coarse grid correction. But in theory, it's all doable for any discretization. But that would be the problem, is it's intrusive. So we'd have to do some work to come up with a specific algorithm for your setting right now. And, yeah, but I think a lot of the ideas would carry over. Yeah.
back to your shifting in paradigm for like parallel in time will eventually come or will eventually be used. You also consider if at some point, as it was done for higher order method in space, there will be also the need for higher order method in parallel to parallel in time, higher order method in time also later.
Say that again, the shifting part, what, I missed the first.
So when you say that in your proof about this new, this.
Oh, that, yeah.
That at some point, there will be a need of parallel time method because of the eventually higher efficiency. Do you also consider that would be something similar as a high order method? I know it was already done at some point, some report, but at some point there will be a need of high order in space because of the shoot. But did you also?
I don't think it matters whether it's high order or low order in space or time. Those are the arguments.
Okay.
In that proof, that proof is pretty simple. It doesn't depend on, you know, specific methods or anything. It just assumes that there is a method, for example, that's polylogarithmic in the number of time points. So, yeah. Wow. Yeah, go ahead.
Again, regarding that proof, I think it makes sense for time critical applications, for example, like weather or something, because there is no use in predicting weather today, later than today. But how do we justify poor parallel efficiencies in other sort of applications, or do you think that it should be agnostic to any application?
So the poor parallel efficiency thing, when people bring that up, I normally just counter with time stepping has worse parallel efficiencies. You can't use the machine, right? So yeah, if you can go faster, you can go faster. I mean, and part of it comes from the multi-grid side of again, multi-grid doesn't have great efficiencies because it's O of n, it's all moving stuff around, right? And so you're never close to peak performance. You know, efficiencies are just not as good as you find in lots of other places. So kind of used to having that be the case, but it's still the fastest often method, right? So it's that can be misleading to focus too much on efficiencies because one way to get high efficiencies is to start with a really bad method, slow method.
Well, isn't it true that when combined with spatial parallelism, you can end up getting better parallel efficiency?